So after the past few videos, we have been looking at where electrons are in atoms, and we've realized that it's gotten a little bit more complex as we've started to figure out that not only can electrons be described as particles with mass and velocity, but they can also be described as waves. And waves in our concept of waves don't have mass, but what waves do have are mathematical equations that can describe them. And so with mathematics, we have been able to predict where electrons are most likely to be found. That model is called the quantum mechanical model. So what we will be looking at today is the quantum mechanical model of the electron. The scientist there are many scientists who contributed to this idea, and one of them was this gentleman, Werner Heisenberg. You may have heard of him. And through physics, through a lot of math, he came up with this idea that there is a limitation on what we can know. And he called this the Heisenberg uncertainty principle. He said that we cannot know the position and momentum of a particle at any given time. And so what can scientists know? Well, we can only know the approximate location of an electron. And what we call those approximate locations are orbitals. Orbitals are the 3D space where an electron is most likely to be found. They are called density maps, and you can see in the picture that in the origin where the x, y, and z axes meet, there's the nucleus, and then around it it's very dark, and as you go out from the center it gets lighter and lighter and lighter. That's a density map. It shows that if you had an electron and this was like a strobe light and it was taking a picture every second, where would it show the electron being? It is most likely to be found close, in that area, sort of closer to the nucleus, and then it gets lighter and lighter and lighter as it goes farther and further away. What we have on the right is just a simplified diagram where we've sort of created a boundary. The boundary is where an electron can be found 95% of the time inside that, but that means 5% of the time it can be found outside of that. There are different shapes of orbitals. The four atoms that exist on the planet Earth and atoms that we've been able to create in a lab have electrons in 4 orbitals, the s, p, d, and f orbitals. Those are different shapes. So how do I read these pictures, right? These orbitals, and what we're looking at on this page are just the s orbitals. They are 3D diagrams showing where an electron is most likely to be found. The orbital is really a probability. That's what we mean by most likely, a probability distribution of where the electron just might be. But what is really interesting about that is it's still just where it might be, not where it is. With the Heisenberg uncertainty principle, we're letting go of the idea of knowing exactly where an electron is. We can know where it is most likely to be found. Inside every orbital, inside any one of these shapes, there can exist only a maximum of 2 electrons. These electrons themselves are spinning. And through the Pauli exclusion principle, we have figured out that they cannot be spinning in the same direction. They must be spinning in opposite directions. So they have to have 2 different spins. Think of it as like clockwise or counterclockwise. They're often drawn with up and down half arrows to symbolize their spin. You're going to draw a lot of those arrows at the end of this chapter. So looking at this picture, you see here's one electron with an up spin, and here's one electron with a down spin. And that's the Pauli exclusion principle. No two electrons can be in the same exact orbital and have the same spin. They must be opposite. So let's look into more detail on those s, p, d, and eventually f orbitals. The s orbital is the lowest energy orbital. It's the simplest orbital. It looks like a sphere. And so that's sort of easy to remember. We will oftentimes put numbers in front of the letters. So you may see 1s and 2s. And what that number stands for is the energy level. The 1s is a specific size, and the 2s is a little bit bigger, and the 3s is a little bit bigger. P orbitals. P orbitals only exist at energy levels greater than 1. So in the first energy level, there's only an s. In the second energy level, there's s and p. And every time we add an energy level, we add a new shape. Even though there was only one variation on the s orbital, there's 3 p orbitals. They have different names based on what axes the orbital is lined up on. So p orbitals kind of look like peanuts. If you think of like peanuts in their shell, they have 2 lobes. And the px orbital is lined up on the x-axis. Here's the py orbital lined up on the y-axis, and then here's the pz orbital lined up on the z-axis. We think of the z-axis as coming in and out of the plane of the paper or computer screen. D orbitals happen when we get to the third energy level. There are 5 of them. So there was 1 s orbital, there's 3 p orbitals, there's 5 d orbitals, and you can see the pattern that's happening here. It's the odd numbers. So how many f orbitals are there? Well, there's 7 of them. 7 f orbitals. The orbital shape gets more and more complex as the energy level increases. Okay, these 3 orbitals, right here you see 3 samples of the d orbitals. On another page we'll show all of them. But the dxy is here. There's dxy, dyz, and dxz. The dxy, the lobe is in between the x and y axes. So think of here's the y axis, here's the x axis, and then the lobes are in between those. They're not right on the axes. Whereas the dx squared minus y squared, now that we have the squareds in there, here's the y-axis and here's the x-axis, and this is a little bit harder to see, but the lobes are more located on the axes. And then finally, the dz squared. This one's strange, but again, dz squared, it has a lobe lined up on the z-axis. Kind of looks like a p orbital. But then there's also this weird donut-shaped lobe going around. We're going to see other pictures with this. Now, summing this all up, each orbital can hold 2 electrons. So that means only 2 electrons can fit in the dxy orbital. Only 2 electrons can fit in the dz squared. They, of course, have to have different spins or opposite spins. As the energy levels increase, the number of orbitals at each energy level and the orbital shape gets more complex. As the energy levels increase, the electrons in the orbital get further from the nucleus. So how are energy levels fitting in with all this? We'll see this in a picture in a second, but the energy levels that Niels Bohr figured out with those atomic emission spectra, remember, he correctly predicted everything about the hydrogen atom, so it's still true. It still has to be true. Electrons can only exist in certain energy levels, which are a very specific distance from the nucleus. And what exactly are sublevels then? The sublevel is another name for the shape of the orbitals within those energy levels. And so here is maybe a better picture of those orbitals. You can see the s orbital looks like a sphere. Those p orbitals look like peanuts, or there's a pair of lobes. And the px orbital is lined up on the x-axis. The py orbital lined up on the y-axis. The pz orbital lined up on the z-axis. Then there's the 5. So 1s, 3p, 5d. There's the 5d orbitals, dxy, in between the x and y axes. dxz, in between the x and the z axes. dyz, in between the y and the z axes. And then finally, dx squared minus y squared, we have those squareds in there. That means that it's on the x and y axes. And this is the strange guy, dz squared, has one lobe on the z axis and then a donut-shaped lobe around the origin. These shapes have been confirmed through experimental evidence and also predicted through mathematics, through graphing equations with x's and y's and z's. This picture right here is just reiterating again the idea that that first number tells us what energy level the orbital is in, and that is a very specific shape, right? So the 1s orbital is the S shape, and it's a certain distance from the nucleus. The 2s orbital, that same shape, but a little bit further from the nucleus. Every shape is in a particular energy level, and that would mean a particular distance from the nucleus. This table really sums up everything. So in the first energy level, there's only one sublevel. That's the S, right? And since it's only one orbital, and each orbital can hold 2 electrons, the first energy level can only hold 2 electrons. In the second energy level, there's 2 sublevels. There's an S and a P. And now look at the numbers. There's 1 S and there's 3 P. So for a total of 4 orbitals, the Pauli exclusion principle tells us that it can hold 2 electrons. So in the second energy level, it can hold 8 electrons. The second energy level holds 8 electrons. This pattern keeps happening. In the third energy level, you have 3 different sublevels, 3s, 3p, and 3d, for a total of 9 orbitals that then can hold 18 electrons. Do you see where I'm getting 9 from? 1 plus 3 is 4, plus 5 is 9. And then finally, fourth energy level, so 4 different sublevels, S, P, D, and F. Look at that number. 1 plus 3 is 4, plus 5 is 9, plus 7, 16. 16 orbitals, each holding 2 electrons, which means the fourth energy level can hold a total of 32 electrons. All this information is going to be gathered together, and we will eventually get to a place where I will be able to predict where, let's say, titanium, where all of titanium's electrons are. That's where this is headed in the next video.